So it's interesting to note that nothing that we've talked about is intrinsic to real-valued vectors. So an obvious extension to this would be something like Hilbert spaces or some general mathematical spaces where an inner product and a norm was defined. So instead of like considering a very general discussion, let's just pick one kind of unusual space and develop something like linear regression for that space. Okay, so imagine the space L201. So this is the space of square integrable functions, real-valued functions on from 0 to 1. So f is in this space. F is in this space if and only if the integral from 0 to 1 f of t dt is finite. F of t squared, f of t squared dt is finite. And let's define the inner product between two elements of this space, f, inner product of f and g, as just equal to the integral f of t, g of t, dt. Okay, so imagine I have a vector, or I'm not a vector, I have a realization of a function that lives in this space. And you can imagine this actually occurring in statistics where, yes, we have a function that we realized where we have an outcome over time, say, for example, but it's recorded on such a fine scale. It's recorded on such a fine scale that it's maybe preferable to treat it as continuous rather than a collection of discrete points. Okay, so imagine we have a continuous function that's in the space of real-valued square integrable functions, and its domain is 0 to 1. Imagine trying to approximate that function with another function, x. So you might think of lots of different approximations that we might try to use, for example, maybe a sine approximation or something like that, where the observed function is something like that. Okay? Okay, so, and we want to try to minimize the least squares criteria, y minus beta times x squared, the least squares criteria. So in this case, it's not dealing with vectors. In this case, this is the integral from 0 to 1 of y of t minus beta times x of t squared dt. Okay? So what's the minimizer? Well, hopefully you'll have guessed what the solution is. The solution is beta hat is equal to the inner product of y and x over the norm of x squared. Okay? And we should be able to prove that pretty easily. And let's do that really quickly. So let's start with the norm that we want to minimize and expand that out. Well, actually, since we know what the solution is, let's add and subtract the solution. So y minus beta hat times x plus beta hat times x minus beta x. So this is a little bit of a cheaty way to do things because we actually know what the answer has to be. So now let's expand our inner product or our norm out to get norm y minus beta hat x squared plus 2 times the inner product of y minus beta hat x beta hat x minus beta of x plus norm beta hat x minus beta x squared. Okay, so you can double check me on working out all those norms. So this is only going to get bigger, this is only going to get smaller if we take this thing that has to be positive and omit it. Okay, so let's do this, get rid of that. Okay. Now we want to work with this inner product here because we can sort of simplify things there a little bit. So let's rewrite this term right here and then work on simplifying this term. Or expanding out, I shouldn't say simplifying, I guess complicating this term in a sense. So 2, and then the beta hat is a scalar, so we can pull it out. 2 beta hat y and x, so that's from those guys, plus, oh, and it's a minus for that, plus 2 beta y and x, that's from that term, plus 2 beta hat squared norm of x squared. Okay, and that is from that term right there. And then I'm just double checking, and then minus 2 beta hat beta x squared. Okay, and that is from that term right there. And I think that gives us everything. Let me get that right there. Okay, so now let's look at these terms and see if there's any further simplification we can do. And let me just make sure I got my minus signs right. So that one's minus and that one's minus, and the other two are plus. Okay, that's correct. So what I'm going to do is actually plug in for what beta hat was. And let's just write over here to remind ourselves the beta hat was inner product of y and x over norm x squared. Okay, so this is going to be minus 2 y inner product of y and x, and then squared over norm x squared. That takes care of that term. Okay, plus 2 beta y and x, that takes care of that term, plus 2, and then if I plug in for my beta hat there, I get 2 y and x inner product squared, and this has a norm of x squared, but when we square beta hat over here, we get a norm of x to the 4th power, so that's norm of x squared in the denominator there, and then minus 2 beta inner product y and x. Okay, so let's see. So this term right here is the same as that term right there, and it's minus 2 and plus 2, so those cancel out. And then this term right here and this term right here are the same, so those two cancel out. So we get norm y minus beta hat x squared. Okay, so looking back, what we see is that this quantity has to be bigger than when we plug beta hat in. Okay, because they're all equalities except for that one where we get a greater than or equal to. So beta hat has to be the unique minimizer of that equation, or at least the minimizer of it. You can show that it's unique. So one very clear case of this would be the instance where x is just equal to 1 from 0 to 1, which is, of course, has a finite integral on that range. Then we get that the best approximation of a continuous square integrable function on 0, 1, the best constant approximation of that, right, is the best beta for that is going to be beta equal to the norm of y and 1 over the norm of 1 squared. Okay, well, the norm of 1 squared on this space. The integral of 1 is 1, so it's squared is just 1, so that denominator doesn't make any difference. So then the top is integral y of t dt from 0 to 1, multiplied times 1, which I'm omitting. So we might just call that function y bar, right? Because remember, if y was a vector, the average was that. So we call that function y bar. Okay, so we've covered regression, regression, the equivalent of regression to the origin, and now the equivalent of mean-only regression. And now can we use this to come up with something that's not unlike linear regression, but now with functions? And we can do that. So let's do that really quickly. So let's ask now the question, and then I think if once I've done this, I think you can see how you could extend this if you had multiple regressors, not just a single one. Okay, so here we have y minus beta naught, and then just to be consistent with the notation I was using in the previous lectures, let me define j as just a function, j of t equals 1. So let's say y minus beta times j minus beta 1 times x squared. So let's see if we can figure out what's the correct functional estimate, the estimate of beta naught and beta 1 when we're doing this kind of functional version of least squares rather than ordinary least squares. So we want to predict our function y with these two functions here, the linear space defined by a constant function and whatever the function x is. Okay, so we can use the kind of arguments that we've done previously to do this. So imagine if beta 1 is held fixed. Okay, then we know that this equation, which I'm going to label as asterisk, we know that it has to be minimized at the point beta naught hat, depending on beta 1, equal to the inner product of y minus beta 1 x and j over norm j squared. Okay, and that's true if beta 1 is held fixed. So you might think of y minus this term as a single function then. So this denominator is just 1. So the numerator is integral y of t dt from 0 to 1 minus beta 1 integral 0 to 1 x of t dt. So that's just equal to y bar minus beta 1 x bar if we define bar as just being the integral over 0 to 1. Okay, so now we can make asterisks smaller by plugging in beta naught as equal to that quantity. So we can make it smaller by plugging in y bar minus, and now beta naught is going to be y bar minus beta 1 x bar minus beta 1 x, and then we can rewrite that as y minus y bar, and times j, sorry, y minus y bar times j minus beta 1 x minus x bar times j. So you can see that it works out to be pretty much identical to when we were developing ordinary regression. So now it's regression through the origin, right, with the centered functional version of y and the centered functional version of x. So we know that that's going to be greater than or equal to if we plug in beta 1 hat equal to the norm of y minus y bar times j and x minus x bar times j over the norm of x minus x bar times j quantity squared. So we could make some further definitions. So if I were to define integral of y minus y bar times j, and I'm omitting the t's, x minus x bar times j dt, if I were to define that as the let's call it the covariance between the function y and the function x, okay, and define the variance of a function y as the covariance of y by itself, okay, then this quantity right here, our slope estimate, works out to be the covariance of y and x over the variance of x, okay? And then if I were to further define the correlation between y and x to equal, this is the standard definition of the covariance over the standard deviations being the square root of the variance, then I wind up just getting that this is the correlation between, the functional correlation between y and x times the functional standard deviation of y divided by the functional standard deviation of x. So we get the same exact answer as we see in linear models, provided we, in ordinary vector-based regression, provided we make these definitions, the obvious definitions for what constitutes a functional correlation, what constitutes a functional variance, and so on, what constitutes a functional mean. Okay, and so now if I were to plug that beta in, then I get a unique minimizer, and my beta hat is defined like this. And then if I wanted to solve for beta 1, or for beta naught, my beta naught hat would just be y bar minus beta 1 hat x bar. Okay, so the broader point of this lecture was to just show you that these same rules that we're developing for linear functions apply in less standard spaces. Like in this case, we basically went through the same arguments that we went through to develop the slope and intercept estimate in vector regression. We just did exactly the same manipulations and came up with a slope and a variance estimate for a functional version of regression where our data and predictors are functions on the space of square integrable functions. And so this also shows that we can obviously develop things like variances and covariances on function spaces in the same way we've developed variances and covariances on vector spaces. So I hope you found this as an interesting lecture. When we get to multivariable regression, we'll do the same exercise, but then with multivariable regressions.